Hi, in this video, we're going to talk about how to implement Kruskal's algorithm. So before I show you my implementation, if you want to practice your coding skill, you might want to write the code for Kruskal yourself first. It is, in fact, I think one of the easier algorithm that you can write, and your implementation can actually stick pretty close to the pseudocode. So here is my implementation. I base it off the graph implementation that we did in the previous lectures on implementing the Dijkstra's algorithm. And I actually duplicate the code and I make small modification to some of the existing classes. And even with that, and with quite a few lines of comments, it's not a whole lot of code. It's just about 120 lines. And so if I have had more time, I probably would have written the graph and the vertex class and the edge class in a more generic way, so that for Kruskal, I can just inherit and enhance from the generic implementation. But anyway, this is what I ended up with, and I'll go through it line by line to explain it. So this is the vertex class, and there are really only two small changes to it. One is I added an attribute tree to each of the vertex. So remember, given an edge, we have to look at the two vertices that an edge connects and see if they're in the same tree. So we have to figure out for each vertex which tree it belongs to. So there are multiple ways to do it. One is for each tree, we can contain a set of vertices, right? And then in order to figure out which tree a vertex belongs to, then we look through all the trees and see, uh, if a vertex is in that tree. Um, that's to me, it's a little bit slow. So a slightly faster way to me is that for each of the vertex, I just have a reference to the tree that it is in at the moment. So that's what this attribute is for. Now, keeping this attribute obviously uses a little more memory. So even though it's faster, it does use more memory. And the second change that I make is that because each tree would still keep a set of vertices or vertex instances, right? So when we use Python set, any element that we put in the set must be hashable, right? That's the requirement for a set. If you remember that from our hash table um, um, lectures. So that's why I have to implement the dunder hash. And to hash a vertex, the simple thing is just to hash the ID, which we assume is unique from the client's perspective. Next, we're going to talk about the edge class. Remember that we talk about minimum spanning tree in the context of undirected graphs. So technically, there is no source vertex or destination vertex, right? The two vertices they are symmetric. Um, However, there are two vertices, and they must have two different names. So I just left the name as source and destination. But again, um, this is undirected edges. And then the next change that's not a change. The only change that I make in the edge class is really again because we have the forest is a set of edges or edge instances. So again, if we want to put edge into a set, the edge must be hashable. So I implement the Thunder hash that returns a hash of the edge's ID. Next, we can actually talk about the Kruskal implementation itself in the graph class. Now, it does use a nested class called tree, and it's a nested class because, well, it seemed to only a tree class only seemed to make sense in the context of graph. We'll look at what tree is in the next slide, but let's talk about the actual algorithm first. I call it the MST, minimum spanning tree method. So, well, first we initialize an empty forest as the pseudocode says, and then for each of the vertices in the graph, we create a tree. Then that tree contains only a vertex, right? And then the next step in the pseudocode is that we'll sort all the edges, right? We get all the edges by its weight. So we just use the built-in sorted function, and the key that we're going to sort by for each of the edge is its weight. And then we remember the sorted edge in, well, sorted edges. And then we go through each of the edge in sorted edges. So we're going through them in the non-decreasing order. And then we find out the two trees that, well, remember the edge has a source and destination vertex, and each of them points to the tree that they're in, right? So we have two trees, and then if the two trees are two different trees, okay, then we merge them. So we merge, in this case, we merge the destination to the source tree. It doesn't matter if we do it the other way around, but we just have to pick one direction, right? And then once we merge the tree, then we can add the edge to the forest. So, and that's it. That's pretty much the pseudocode, but in actual interpretable or executable Python code. And then finally, we will kind of transform the forest, the information that's in the forest, into something that the client that is suitable for the client. And the way that we do that is that, and remember, what's in the forest are edges, right? We add edges to the forest. Now, we don't want to expose the edge class to the client because, well, edge class to me is internal to the graph. So, in order to not to expose the edge class, but still return something that is kind of like an edge, we basically just convert the edge class into tuples of this source vertex of the edge and the destination vertex of the edge and the weight of the edge. And we put these tuples in the set, right? And that's what we'll return. And the last thing we need to look at is the nested tree class. And so remember, when we first instantiate a tree, we instantiate the tree with a single vertex in it. So that's what the initializer will take, a single vertex. Now, a tree ultimately will contain a collection of vertices, and the order for these vertices do not matter. So that's why the vertices is a set. And the first vertex that we put in the set of vertices is obviously the one that we start with. And this vertex then, the tree that it's in is obviously the self tree that we're initializing. So that's the initializer. And the only other significant operation we have to support for tree is the merge operation, that we are merging the self tree with another tree. And the merge operation, if you look at the two trees, all they contain are a set of vertices, right? So therefore, when we want to merge the two trees, then we are basically building a union of the vertices in the self tree with the vertices in the other tree. So that's what that union is for. And then finally, because now these vertices in the other tree. They are now in the self tree, so we have to update each of the vertices in the other tree. We have to update their tree attribute to the self tree now. And the other two method is basically there for to support debugging as usual. And that's it. That's all the code. And as I promised, it's not a whole lot of code, and it's actually very, very close to the pseudo code. So now that we have an implementation, as usual, we should do the testing. So the test that I wrote for this, the one test I wrote is the example that I demonstrate earlier, and that is this graph. And you can kind of see I kind of just spell out just the name of the graph, all the vertices, and then all the edges. Okay, and then the expected return from running the MST on the graph would be this, and that would be these the set of these thick edges, and I just make sure that what it returns is what we expect. And I can run this, which I already typed out, and if I run it, yeah, as you can see, it ran successfully, which gave me some confidence that this implementation actually works. And I also want to just say something about from the software design perspective, that if you look at the way that we specify the graph, so this is basically the input to the graph, right? And also the return result from running the Kruskal's algorithm. So if you look at these two, they are really kind of very similar to each other, right? And also, as I've emphasized when I was talking about the implementation of MST, I do not want to expose the client, which is the test code here. I do not want to expose the client to the edge class. That's why I actually went to some length to convert the edge class into this tuple of edges that looks just like the input that specify the edges. And the advantage of that is that I can actually completely change the internal implementation of graph. Then maybe, at some point, I don't even want to have an edge class. I can change that, and the client would not be affected at all, because the edge class and any other internal implementation detail of the graph class is never exposed to the client. All right, so having shown the implementation and having done a single test, I think it's your turn to write a little bit of code that you've worked out the MST for this graph before, and now you can actually write a test that specify this graph and then run the Kruskal's algorithm, and hopefully the code would give you the same MST as you've kind of figured out when you do it by hand.